All right, the converse of the Pythagorean theorem basically says that, if you can go and say you got a right triangle, you have a right triangle, then you would know that the legs squared would end up being the hypotenuse squared as you add them together. So the converse is going to be the backwards approach, so that if you have something and you're looking at a triangle, but you don't know if it's right. Maybe it's like this, maybe it's actually right. But you can figure out a squared plus b squared, and then you can figure out c squared, the longer of the three legs, or three sides. And if they're equal, then you know, well, you got a right triangle. And if they're not equal, then you know you have something else, but definitely not a right triangle. I think it's somewhat self-explanatory, but if A and B are measures of the shorter sides of the triangle, and C is the longest side, and the reason they say longest side, they can't say hypotenuse, because if you use the word hypotenuse, that would assume that it was a right triangle, and you can't say that. So if those A and B are measures of the shorter side, and C is the measure of the longest side, and you square them, and they end up being equal, then you got a right triangle. If they are not equal, then it is not a right triangle. And you can't get any more specific than that, and that's fine. It doesn't tell you if it's obtuse or scaling or things like that. So check for right triangles. Determine whether the following side measures form right triangles. So if I look at number 1, as you do these in homework, it would be nice to have the sides rewritten. And the other thing, you probably don't want to draw it, but you can. And so if I sketch this, I'm going to end up making a right triangle, because that's what we're testing out here, where that's 29, that's 20, and that's 21. But I'm definitely putting 29 on the side that would be the hypotenuse. On these, rewriting the formula only takes another second. So I have 20 squared plus 21 squared is equal to 29 squared. And I'll type some of these into the calculator. I know this is 400. Just know that. I know this is 441. That one I had to type in. Now, 29 squared I definitely don't know. That gives me 841. Now, when I add up the left side, I get 841 equals 841. And as far as our organization of this problem goes, it's kind of nice to put a check, because we ended up getting a true statement. And so to summarize this, I say yes, it's a right triangle. And the way we can abbreviate that is yes, comma, A, RT for right, and then triangle. Let's see. Probably just one more of these is enough. So I'll do problem 2. I have this whole 8, 10, and 12 to look at. And I know I'm testing out if a squared plus b squared is c squared. And as I take a stab at this drawing, there's a shorter looking than 10. And then over here I'll have 12. And then I'm going to plug in the shorter sides. 8 squared plus 10 squared is equal to 12 squared. And I don't like to jump to those answers. I like to see it worked out. 64 plus 100 is 144. And then when I add 64 and 100, I get 164. And then on the right side, I get 144. And what we figured out is that this does not equal each other. And so now that I know that, I'm probably going to back up my slashes so that I say these are never equal, if I really wanted to be clear. And then as I summarize this, I'd say no, it's not a right triangle. I think that that's enough. Finish problems 3 and 4 on your own. And you got 10-4 Pythagorean Theorem with a bunch of different problems. And I think this section should go pretty well.